this video, we're talking about the interesting thing that happens when two chords intersect one another inside a circle. So if we look at this first figure here, we have a circle, and we have two chords in the circle. Remember that a chord is basically just a line segment that's inside of the circle that has its endpoints on the perimeter of the circle. So for example, this line segment here, line segment AB, is a chord because it's just a line segment inside the circle with each endpoint, endpoint A and endpoint B, on the edge of the circle. So we have chord AB and we have chord CD, and they intersect each other at this point here in the middle. So when we have two intersecting chords, here's the interesting thing that happens. You can take the two measurements of each segment of the chords. So for example, chord AB, this portion of it up until the intersection point, starting at A and up to the intersection point, is 10 units. From the intersection point to B, we've got 8 units. So the total length of the chord is 18. But if we multiply 10 by 8, we can actually set that equal to the product of the lengths of the segments of the other chord. So in other words here, let's look at the two segments for chord AB. Well, that's 10 and 8. So if we say 10 multiplied by 8, we can set that equal to the lengths of these other segments for chord CD, which are x and 16. So we'll do 16 times x, and then we can solve for this unknown value of x. So we get 80 is equal to 16x. If we divide both sides by 16, we get x is equal to 5, and we can go ahead and say that the length of this segment here from C to the intersection point is 5. So that's the unique relationship that we have between intersecting chords within a circle. We can do this here with another example. We have chord QR and chord ST. We know these lengths 9, 6, 4, and x. So if we look at the chord QR, we have lengths 9 and 4, so we'll say 9 times 4, and then set that equal to the lengths from the two segments of the other chord, 6 and x. So 6 times x. That's going to give us 36 is equal to 6x, and dividing both sides by 6, we get x is equal to 6. And we can even do this when we have multiple unknown lengths. We just take the two lengths from chords EF, so x and x minus 2, so we'll get x times x minus 2, multiply those together, set that equal to the product of the lengths from the other chords, so 3 and 8, so I get 3 times 8. When I multiply out here, I'm going to get x squared minus 2x is equal to 24. If I subtract 24 from both sides, I'm going to get x squared minus 2x minus 24 is equal to 0. Now I can go ahead and factor the left-hand side. So I'm going to get x minus 6 times x plus 4 when I factor, and then if I set each of these factors individually equal to 0, I can say x minus 6 equals 0, or x equals 6, and x plus 4 equals 0, or x is equal to negative 4. So I have two possible solutions for x. I need to test them in my circle here to figure out which one is the correct solution. And I can see right away that x equals 6 is going to be the correct solution because I can't possibly have a negative value. This distance here from E to the intersection point along chord EF, this distance is x. Well, I can't have a distance of negative 4. That's impossible. You can't identify a negative distance. So x equals negative 4 can't possibly be a real solution to this problem. That means that x equals 6 is going to be the unknown value of x. And if we want to go ahead and plug in here, we can say that this length is going to be 6. When we plug 6 into x minus 2, we're going to get 6 minus 2, or 4. So we can say that this length is equal to 4. And then if we just want to double check ourselves, we should be able to say 6 times 4, or 24, is equal to 3 times 8, or 24. So in fact, it does check out as a value for x that satisfies this formula of intersecting chords.